So exercise 10.01 is about the scalar product, which is also called the dot product. So it is a method of multiplying vectors. It applies the directional growth of one vector to another, and we'll come back to what that means. That's a bit tricky to get your head around, but we will see that. The result's a scalar, not a vector, so it's just a number. It doesn't have direction. And to calculate it, this is a formula here. To calculate it, there's more than one formula. So just x1 times x1 plus y1 times y2. Simple as that. So if we look at these vectors that are both horizontal vectors, so we've got the vector -3, 0, and the vector 2, 0. We multiply them. It's like multiplying 2 times -3. It applies the negative direction, and 2 3s are 6, so that's what we're going to get. So let's have a look at that. So 2 times -3 plus 0 times 0, so -6 plus 0, which is -6. So the direction, if you think of this vector as your base vector, you're applying the directional growth of this onto that. The direction is that way with a growth of a factor of 3. So 2 becomes -6. Just looking at just this simple one here, so multiply the top, 8 times 2, add it to 1 times -5, and we get 11. So that's just a simple example. You might be given the vectors in component form. So it's just 2 times -7 plus 3 times 4, and so that one equals 2. And you may also be given your vectors with a bit of trigonometry in there, but just convert the cos 45 and the sin 45 to 1 on root 2. They're both 1 on root 2. So A is the same as 3 on root 2 over 3 on root 2. If you couldn't do that, it'd be slightly more complicated. You'd be adding some trigonometric things. There could be some difficult things there, but it's just try and follow logically through the steps. So if we multiply that vector by itself, finding the dot product of A with A, and then it's like squaring. So when you multiply the top, you're squaring the top. You multiply the bottom, you're squaring the bottom. Square them, add them, 9 on 2 plus 4 on 2, which is 13 on 2. So we get this interesting thing happening here. So if u is the vector xy, then u dot product with u is xy times xy, so x times x and y times y added together. But also if you remember the magnitude, so the magnitude is found with Pythagoras' theorem, the square root of x squared plus y squared, but we're squaring it here, so we don't need the square root anymore, so just x squared plus y squared. And those two things are actually equal to each other. So we get this useful rule that the dot product of a vector with itself is actually equal to its magnitude squared. Now, as I said, there are two formulas for the dot product, and this is the other formula. We've got the dot product is the magnitude of u times the magnitude of v times the cosine of the angle between them. So I'm going to prove that, and we actually prove it with the cosine rule. So I've drawn this diagram over here. So this is our vector v, this is our vector u, this is the angle between them. And then this vector here is u minus v. Now remember, when you're subtracting, it's pointing that way. It's that one minus that one. So it's the vector u minus the vector v. And we're just going to apply the cosine rule to that. So the length of this side squared is equal to the length of this side squared plus the length of that side squared minus 2 times the length of that one times the length of that one times the cosine of the angle between them. That's on our reference sheet. Now, just looking at this, we just said here, we said here that this thing here, the magnitude squared is equal to the dot product times itself. So we can rewrite this like this, and we can do the same thing with those two. So the magnitude of v squared is the dot product of v with itself. The magnitude of u squared is the dot product of u with itself, and then just that last bit as well. With that left-hand side, we can just expand it out just like normal expanding brackets. So u dot u is our first term, and then it's minus 2uv, u dot v, and then v dot v, of course, at the end. And I'll just write that whole right-hand side again. Now, what we've got here is some things that cancel each other out, so we can subtract u dot u from each side. we can subtract v dot v from each side, and that leaves us with negative 2 u dot u is equal negative 2 the length of u times the length of v cos of the angle. Divide each side by negative 2, and there is our formula. So that's that proof of that formula. It's a very useful formula to know. I actually can't remember if it's on the reference sheet. Check that. If it's not, you might want to write it down somewhere. If you're keeping a list of formulas that you need that are not on the reference sheet. So let's look at this example. So we've got a vector with a magnitude of 3, another vector with a magnitude of 5. The angle between them is pi on 3, and we have to find the dot product. So let's write the formula and just substitute in those values. So 3 times 5 cos pi on 3. Now, 3 times 5 is 15, cos pi on 3 is half, so 7.5 is the answer there. Now let's consider that statement that we were talking about. The dot product applies the directional growth of one vector onto another, and we'll use this one as an example for that. So there's our vector u, there's the angle theta, so v is up there, so that angle is pi on 3, which for those of you who like to think in degrees, that's 60 degrees, so I've drawn it to be approximately 60 degrees. U has a magnitude of 3, V has a magnitude of 5. So if you draw a line straight down here, U will go slightly further across. Let's just consider this triangle here, of course. If that's 5, then this side will be 5 cos theta, the adjacent side, when that's the angle. And this is 5 sine theta, the opposite side is the sine. So 5 cos theta in this case is the horizontal. Because I've drawn u horizontally, we don't know that u is horizontal, but because I've drawn u horizontally, the component of v in u's direction is 5 cos theta. So 5 cos theta is that distance there until we're directly under. It's that distance, and that's been multiplied by the length of u. So this distance multiplied by the length of u is our dot product. So that's what it means by the directional growth. Just the part of v that's in the direction of u is increased or multiplied. It could go the other way, but it's multiplied by that. That's what it means by directional growth. Okay, let's just do another example where we have to find the angle between these two vectors to the nearest minute. This is quite a common type of question that you might get, and it's just a simple application of that dot product formula. So there's our formula. Now we will need to find the length of u and the length of v. The dot product is, of course, the 2 times 5 plus the 3 times minus 2. So 2 times 5, 3 times minus 2, and the magnitude of u is the square root of 2 squared plus 3 squared. The magnitude of v, so that's 5 squared plus negative 2 squared. I often don't even worry about writing that negative there. Just 5 squared plus 2 squared is fine. Times cos of the angle between them, and it's that angle that we don't know, so that's what we have to work out. So let's work out this product. So we've got 10 minus 6, so that's 4. I've worked out those square roots, so 2 squared plus 3 squared multiplied by 5 squared plus 2 squared gives me 377, still under the square root. So I actually multiplied this by that and left the square root in there. Divide by the square root of 377 to get cos theta. And switch it round, and then of course cos inverse. So theta is cos inverse of that, which is 78 degrees and 7 minutes.